All right, let's take a look at the next part of the handout 133 M511 on the outline. So we just had completed or just had finished looking at handout 31. I'd like to take a look at the item 9b, which is we're going to take a look at a simple R22 system. So I'm going to go to that PowerPoint that's in your lecture materials, and we'll take a peek at that. So on this particular system, on a simple air conditioning system, what we're going to be taking a look at is basic operation of a compressor. We got a metering device. We're going to have a couple of tanks. They're going to represent the evaporator and condenser. So think of those as like a heat exchanger for each side of the system. And we'll have high and low pressures identified with some superheat and some subcooling. So on my system, compressor up on the top and in the middle. So we're going to have the two tanks. We have one side over this way, one over this way. Those two tanks are going to represent the metering device, or the condenser and the evaporator. So on the left side, being that we have a 95-degree ambient surrounding the condenser, that would pretty much mean that we're going to need to make sure that my condenser is going to have a warmer temp than the 95 degrees, so I can reject some energy or give that heat to the cooler outside air. Even though it's 95, I still have to be able to do that. On the right side of the illustration, we're looking at that tank representing the evaporator. And being that we are looking at an air conditioning system with 75-degree air, that would mean that we're going to need to have an evaporating temp that's going to be cooler than the 75 degrees. So we're going to take a look on the left side now. So on this condenser, we're leaving the compressor, we're going to have a saturation temp of 125 degrees. So that between the 125 and the 95, that's going to give us about a 30-degree delta T. Now that's kind of my typical design type conditions that I would normally expect to see on a condenser. Now in this particular case, we're at 175 degrees on the gas side of things. That's the hot gas leaving the compressor. And by the time we leave in this line and we make our way all the way into that condenser, that hot gas has to be cooled down to the point where we can reach let's call it a saturation temp. So we're gonna cool it to the 175 down to the 125, and it'll be all vapor. It'll be a liquid vapor mix. It'll be a complete liquid by the time we are done with this. And of course, that's my latent energy, or what we call my change of state, that has to occur. Then I'm going to take a part of my condenser and we're going to subcool it. So up on the top here, we're actually going to be what we would call desuperheating. And on the bottom, we're going to be subcooling, as illustrated. Now, that liquid will come into the metering device at 115 degrees, and of course it has to drop its pressure. So the pressure in this case, we're saying it's going to drop down to 69 psi, which gives me a boiling point of 40. So the 40 degrees, 69 and 40, so that means the actual temperature of this refrigerant is really 40 degrees. Now as I progress through here, I'm still at 69. I've got some liquid and I got some vapor. And what I've got to do in the entire evaporator, if the evaporator is really doing its job, is that evaporator is going to have to boil off 100% of the liquid into a vapor is what's got to happen. And as you're seeing it change from a darker blue to a vapor to a complete vapor, that's the point where we say, okay, that complete latent energy that occurred there, we saw that change state. Now we're all vapor, and at that point we should be able to even add a little bit of extra superheat, thus giving us a temperature change from 40 up to 50. And then of course we will enter the compressor at 50 degrees. So that's kind of what is going to happen on a very, very basic system to some extent. Now in this picture, or in this illustration, we are showing that we have a total of 10 degrees of subcooling, the 125 minus the 115, and we're showing 10 degrees of superheat, basically going from the 40 degree saturation temp to the actual measured temp of 50. That's 10 degrees. So it's a pretty basic system on there. So it's a very, like I said, it's a very, very simple system. Nothing too complicated on that particular image on there at all to some extent. So in the next system, we're going to take a look at just another little blip of things. And what we're going to do is just show a typical, kind of a, let's call it a lower efficiency system of 10 SEER. SEER is a rating system that we use for identifying efficiencies of air conditioning and refrigeration systems. And we're going to be using a fixed metering device with refrigerant 22, and we're going to look at a 95 degree outside condition with 75 degree is the way we'll set that up. So, all right. So here's another case. So instead of the tanks, now we're going to show with tubes. And of course, leaving the compressor, we're going to show, in this particular case here, we can see, we'll start out, I guess, at the evaporator. Through the metering device, we're at 6940. Evaporation is starting at that point right there. We are going through the evaporator. By the time we reach the point where we're all vapor, and in real life, we don't really know specifically, we can't see inside the tube. So we can only take advantage of this measurement to recognize, are you really a vapor or are you not a vapor? And that's the key thing that is really important in this. So in this case, we're showing a 10 degrees of evaporator superheat. Now, by the time we get back to the compressor, you might have noticed that we are already up to 60 in this line. So what happened now is we would have had to have picked up an additional 10 degrees of superheat in that line. And this happens quite frequently in real life, is that in an air conditioning system, you may have one of your copper tubes that may be picking up some heat due to the warmer outside or the warmer ambient that might be in the facility or in a building. So not uncommon to see that. So in this case, we're showing an evaporator superheat of 10 degrees, but a total superheat of 20 degrees. And that's simply because by the time we picked up in this line, we picked up some, what I'm going to call just some extra heat that was that is in the, let's call it in the suction line. All right. So we are up to the compressor right now. So we've done the low side. Now on the high side, just like the previous system, we had 278 psi, 120 degree saturation temp. So the 278 psi really just told us what is your condensing temp. What is the temperature where the refrigerant will either boil or condense at, is what's going on. So that's kind of the deal with that. We left the compressor at 175 degrees. It's very superheated because our temperature is way higher than the condensing temp, and that's so typical. In this case, condensing is going to start only to the point where we drop it down to the actual temperature of 125, where we can say that is my condensing temp and it should be going. And by the time I get out of that condenser, I will have been fully condensed. At least that's what we would expect it to be. And the way we're going to know it is we're going to know it because the actual temperature will be colder than what the condensing temp is of 125. So when we compare those two, it's showing me 10 degrees of subcooling in this example. So from the 125 down to the 115, thus condenser subcooling is 10 degrees. Now, and that's really the whole process of how that happens on a system. Now, if we take a look at even, let's say, a refrigeration system, comparing, so the last two we looked at were just really air conditioning systems. Now we're going to take a look at on the refrigeration side. And what does it look like? So for the most part, the biggest thing or the biggest difference is the fact that we have a much lower indoor space temp. On the high side, it'll be very much the same. It'll be very close to the same, but on the low side, it'll be much lower, because refrigeration, you're typically not going to be maintaining 75-degree conditions in most spaces. So that's kind of the deal on that. So let's take a look at this one. So here's an example of a little walk-in refrigeration unit with a thermostatic expansion valve, and it's going to show a receiver. And on the high side, we kept everything the same, so pretty close to the same. So we've got our 10 degrees of subcooling. That's, again, we're looking at 125 to the 115. We have a component called a receiver. That's this component. And then as we travel into the low side, remember our box temp is 35 degrees. So that means we've got to make sure that the evaporator temps are colder than the box temp, or you'll never be able to get heat to transfer. So the key here is heat only flows from a warmer substance to a colder substance. And since an evaporator, you want to evaporate refrigerant, you need to somehow get that evaporator temp has to be colder than what you're trying to cool. And that's the only way that it'll do that. So that when we say the refrigeration evap temps are colder or lower than air conditioning, the reason is because of what are you trying to maintain. And that's really the primary way we do that. In this example, I'm going to use a 25-degree evap temp. And in this case, that gives us a delta T on the evaporator of 10 degrees. So 35 minus the 25 is the way that that's set up. But again, very, very basic systems, but those are the things that are going to be your challenges to try to understand, is this normal, is it not, what do we have, and how do we make it more efficient? And those are the key things. All right, so we're going to go back to the, there we go. We'll go back into the module and kind of progress from there. So in the module, we just ended up with item B, looking at that simple system. And you can refer back to those at any time. We're going to take a look at, I think, the operation of looking closer at some of the details of some of these parts and pieces, specifically of basically a recip compressor, a piston type compressor. And we're going to take a look at those things that are in there. So what I will do is I'll pull up the PowerPoint related to that, and then we'll get into some of those things, and we'll delve into this. So in the lecture materials, we have item number 10, which is going to be the compressor. So I'll open that one up, and there we go. So we've got each of those. All right. So in looking specifically at a compressor, one of the first things that the compressor is going to have to do is it's got to pump refrigerant vapor, and it can only pump vapor. It does not have the ability to pump liquids. Its job is to raise the pressure and the temperature of the refrigerant. And those are two very important functions. So looking more at the operation. So the reciprocating, the term reciprocating simply means it's the transfer of a direction of force. So we go from a circular motion of that motor to the crankshaft, to an up and down motion to the pistons. And then there are going to be some key parts of this, let's call it, of the compressor operation, of the reciprocating operation. So the first thing is we're going to have an intake stroke where we're going to pull the piston down. We're going to lower the pressure. We're going to open up a suction valve, and we're going to allow vapor to enter the cylinders to allow that refrigerant vapor to go into the cylinders. So that's the first thing that happens. So here we are looking at a recip type crankcase. In this case, it's showing the, let's call it the, we have a concentric, very much, it looks a lot like an engine, like an inline engine to some extent. So the crankshaft goes round and round and round, and you have concentrics that are on these compressors. And the pistons are going to be moving up and down to illustrate what's happening in there. And of course, every cylinder would be going up and down. At least that's what it's supposed to do. Now we're going to look at some of the more specifics of the Copeland compressor. So we have a couple of images that are in your outline. We'll put some notes on in here in a little while. I'll try to go through this particular set of slides here to illustrate this. But so we have what we call a downstroke, and you'll notice on all of these slides they're going to show parts of the compressor obviously in a simplified manner, but the downstroke simply means the piston has lowered to make the space or the volume smaller in that. Now, by me lowering that pressure in this cavity up in here, by lowering that pressure, that allowed this little valve to open up. And that's basically, we're going to call that a reed valve. And it's a certain type of a compressor valve that allows us to look at it. So as that suction vapor as the pressure lowers, the suction vapor is allowed to move into the cylinder and go into that open space. So that's one part of the pie. So we know we want vapor for sure going into that. We know that we need to move that volume into there, and the only thing that moves, why it moves, is because the pressure in this thing has to be lower than the pressure. The pressure in this cylinder here, in this whole space here, has to be lower than the pressure here. So we need it. That's the only way you're going to get anything to move in there. So what about at the end of the cylinder? So when in the previous one we looked at our cylinder is all the way to the bottom. Okay. Now at the end of the intake stroke, we know the piston is at the bottom. The cylinder pressures are going to equalize, and then the valve will actually close on the intake. So that intake reed valve that I had showed you, that was going to close, allow that valve to close. Now at that point now the piston is at the bottom, what we call bottom dead center. So in this particular case. So when we are at bottom dead center, you're not able to make the space in that cylinder any smaller or any bigger, because you're not going to be able to lower the pressure anymore. So it's one of the gas laws where as I would make a space bigger, so in this case originally when we started up here the space was small. As the piston moved down, we were able to make the space bigger with the same volume in there, and of course that allowed the pressure to decrease. And when it decreased, that allowed the valve to open up and let new refrigerant come into there. And that's really what has to happen to move things, to get it to flow. So that's kind of the first part that's got to happen. Now, in the compression stroke, that's going to be the next phase. So once we reach bottom dead center, we're going to allow that piston to rise up. The pressure will go up in the cylinder. The discharge valve has to open up. So as we move that cylinder up, look at what we're doing to the space. So one of the gas laws says is if I decrease the space or the volume, that the pressure would indeed rise. It's a little bit of common sense on there. Now as the pressure rises enough, what's going to happen then is this little valve, that little reed valve on top there, that's got to open up. So piston's at the top, we've got enough pressure, the valve is compressed, that valve better be opening, and then it's going to go into the condenser, so it has to flow out of there. So that's kind of the typical process of what's got to happen. So compression stroke, piston's at the very top, the pressure's equalized, the discharge valve closes. Once we reach what we call top dead center, the discharge vapor would be trapped in the clearance volume. Now, we're going to talk a little bit about that, and I'll show you. That clearance volume is kind of that, let's call it that unused space that is in between the top of the piston and the valve area. So, and that is actually what I would definitely call an inefficiency of the compressors. So every compressor has a certain amount of that, let's call it that inefficiency, that space that is going to be, has to be re-expanded. So this right here, that concept about the re-expansion, That is so vital to understanding why things happen the way they do in these refrigeration systems, and why we see, the bigger the clearance volume is, the lower the efficiency. So those are all things that typically happen. So again, we'll go back to that compressor now, and here we're looking at, here's the piston at top dead center. Now I can't make the space smaller because of what's going on, and here we're identifying the clearance volume, and that's the inefficiency. So we need a little bit of space there. Now what's going to happen now is that valve will close because there's no delta P anymore. So in this case, as we progress through here, now we start the downstroke again. Now the only way you're going to get any new gas to come in, the only way, is we've got to somehow be able to re-expand that pressure in that chamber, and we've got to make that pressure low enough in that chamber by making the space big enough that the suction valve can now overcome and allow new refrigerant to flow into there. So the pressure in this case has to decrease. It's what's got to happen in there, and that's the forces that will occur in each of those. So on the downward stroke, piston drops, the vapor's pulled in, your pressures are going to equalize, and now you're all ready for compression or refrigeration again. So again, piston's at the bottom, your cycle's complete, the valve closes, now we start the compression stroke. And of course, once the compression stroke goes, then obviously that means the valve should have been closed. We compress it, we discharge it, and we keep going over and over again. So in this example, you can see the process of happening. So that we are compressing, we're opening the discharge valve, we re-expand, we allow new gas to come in. And there's always that little, let's call it delay or change, where there's nothing going on because of the re-expansion, of the inefficiency. And that's just a difficult, that's very difficult for reciprocating compressors to minimize or to eliminate that. So that is just a characteristic of these systems. And every system will have a certain amount. Now, one of the other things that we can hit up on a little bit is with compressors. One of the key things that would go on here is if in the event that there would be some liquid refrigerant that would make its way into a piston or into a compressor, the damage is catastrophic. It can break valves. Like these are two images of reed valves, and you'll notice that the reed valve, normally this should come out all the way around here, and what happened is the reed valve it's sheared off. So that section literally probably from here is probably broken, and that's snapped off. This picture, in this picture, we can actually see from the chattering of the valve, and you can see that little ridge all the way around there, and that's kind of an indicator that the valve, from tapping or excessive pressure on it. So those are a couple of examples, but that's really a very dangerous thing. The way we minimize that in all of our systems is we just try to have some superheat. We try to have a very minimal amount of superheat to maintain efficiency, but enough to make sure that we don't have any slugging. And so that can be really, really damaging. Slugging is simply when you have liquids that go into the pistons and create some damage. All right, so we're going to get into, to keep moving on this, we're going to look at the operation of that system. So a couple of things that I'm going to point out on here. So on my image, that is on the lower part of this. So on my image, what we're going to do is we're going to point out and we'll document and write down a few little things that are going on here. So from the first part is we have a crankcase, the oil return crankshaft, and oil sight glass. So we're going to identify those parts and pieces. So first of all, the crankcase. So the crankcase is actually going to be this, let's call it this piece over here, or this whole space that's inside of there. So we're going to call that crankcase. All right. And the next thing that we're going to show is the oil. So this one I'll identify as the oil on the bottom of this. And as you can see, there's also oil that's even right up on top here. And that's to be expected. As the oil travels through the system, we'd expect it to go back into the compressor. We also happen to have a crankshaft. And the crankshaft would be shown or identified in this particular case as this part of the piece right there. So that's actually going to be called a crankshaft. Okay. Now, the other thing that's identified here is the oil sight glass. So now, not all compressors have this. So in this case here, we have a little glass or a little window. So from the side view, we'd be able to see what the oil level is. And in this case, we're showing it right up there. So that's actually going to be what I'm going to call the oil sight glass. Now that is not to be confused with the sight glass that would be shown in the refrigeration system. It's different purposes, different functions. All right, now item B. So from up above. So right now we've addressed the crankcase, the oil return, crankshaft, and oil sight glass. Oil return, I should probably mention that. So the oil return is really right here. So every compressor has to have some mechanism or some provision, and I'll mark that there as oil return. So as the oil and the refrigerant travels back into the system, we know there's going to be some refrigerant, we know there's going to be some oil. We hope the oil will be dense enough and heavy enough that it'll drop into this little cavity, which is right in this area. And this little cavity should allow the refrigerant to flow right down into the crankcase. And that should indeed happen. And of course, it's very much needed because you've got to be able to lubricate the pistons and the cylinder walls and those things. So oil return is pretty important. Item B from above talks about the piston, the connecting rod, and the wrist pin. Now, the piston, okay, so let's do this here. We'll change to red. So in this case, the piston, we're going to identify that here. So in this case, we'll put, that's of course going to be my piston. We're going to have a wrist pin. Now the wrist pin is actually the piece that goes in between the connecting rod. So I'll mark that out here. So that's going to be called the wrist pin. Okay. Those of you that have played around with engines, that's all basic terminology. Connecting rod. And the connecting rod would be, of course, this piece. So if this right here is my connecting rod. So the connecting rod has to be connected to the crankshaft and to the piston via the wrist pin. So we pretty much have items A. Whoops. We've got items A, items B taken care of. Item C, compressor head. So the head of the compressor, in this particular case here, we're going to get that one going. So the compressor head is actually, let's go ahead and do this. So that is actually going to be what we're going to call the compressor head. Okay, so that's really the top of the compressor. As a general rule, we call it the head of the compressor, the head cylinder heads, you can say. Now, in the compressor head, typically, and I'm going to even make a note on that one too. So in the compressor head, right below that, so right below the head is a valve plate. Now the valve plate is where the suction valves and the discharge valves are going to be held. So we'll take a look at those. Now, in the PowerPoint we looked at a reed valve and how the delta P is what opened that valve. Now that's really important to understand that. Now the suction valve, or I would say the suction valve in this particular case, I'm going to identify right here. That's that valve, and that's going to be my suction valve. And of course, this one here would be, that one right there would end up being my discharge valve. All right, so just like we had showed earlier, and of course, what opens up the discharge valve? Well, it was having a pressure difference, having a differential, and that was the key. That was one key thing. So, suction valve, what opened it? A differential. What opens the discharge valve? A differential. So that's kind of the skinny on there. So the flow, if you look at this image, you'll see the flow has to flow that way, and the flow can only move this way. At least that's the way it's supposed to work. All right, service valves. The service valves, item D. So on item D, the service valves are King's valves. They, we make a note on here, and use a refrigeration wrench only. There are so many times in the field that you'll run into systems where you can tell somebody used a channel lock, or they use a pliers, or they use an adjustable wrench. And what happens is all of those service valve, let's call it the stems of the service valves, they end up getting all rounded or damaged. I've seen jobs where guys use a channel lock on the rounded part even, and it literally damages the service valve, let's call it the gaskets inside the service valve when you turn them in and out. So it's really damaging on there. So in the lab, we will be only using refrigeration wrenches. So, all right, moving on. The suction service valve. So suction service valve right there, suction service valve, that would be this one. So I'm going to make a note on that one. This little device here is called the suction service valve. And what the part that I was referring to, that is where we would use the refrigeration wrench, is right there. That's that little square part typically is the way that works. Now, the next one we'll take a look at is the discharge valve. So the discharge service valve is in this picture it's shown as the right side. So again, I will note that, and that is going to be my discharge valve, discharge service valve. Okay, discharge service valve. So that discharge service valve, it is also kind of a reed type valve, and same thing applies in here. Now, there's a note up on top here, and I'm going to highlight that one again, and there's one major note to make. Whoops, highlight. I'm going to highlight that just like that. It says on here to never front seat during operation. Now let's talk about front seat and back seat and all these positions on these devices. So the first thing that I'll hit up on here right now, down below here, okay, this one is shown this way, and I'm going to go ahead and do this one in blue over here. So right now, this position shown there, that service valve is what I would call back seated. Now, this is really difficult for most technicians to remember what position to put the valves in, to do what. It takes some practice and some experience on this. So it's in the back-seated position right now, where that seat is brought all the way back, is the way it's set up. Now, there is also what we call a front-seated. Now, you'll also notice on this side, we're also shown in the back-seated position. Now, the beauty of that back-seated position is it actually blocks off this port, which is good because that allows me to take my gauges off when I'm working on a system. On the far right side, it is also shown in a back-seated position. But what does that mean? So what we're going to say is this, is that when they say do not operate it ever in a front-seated position during operation, front-seated would be this moving up to this position where it would actually block off that discharge. Now, the problem with that is if we move this all the way into that position, there's now no place for the refrigerant to go. So if this seat would be moved up to this spot, that would actually be what we call front seated. And what would be happening is we would be blocking off that discharge line. That's a serious problem to have. We would not, in fact, any compressor that would have that would either be catastrophically damaged, or if they're lucky enough to have an internal pressure relief inside of it, it would probably blow. But that's a major deal. So this is one of these where most of the systems that have a discharge service valve are usually just on your, let's call it your more advanced systems, or your systems, commercial refrigeration, things like that, they would expect the technicians to know what they're doing, is primarily probably the way we can look at it. So that's kind of what we mean by that. Now, moving on. So, all right, so we've addressed the service valves, item D. A couple of names for service valves would be, would be the king valve or service valve, and we'll get into the more of these on the systems. We have those on our trainers. Operation of the compressor is vapor only. You know, we have a suction, we have a compression stroke. Now you remember when we went through that in the video or in the PowerPoint, the suction stroke was where we brought new gas in, and the compression stroke was where we were compressing that gas, is the way that was set up. All right. Now, one of the things that also is going on, you know, they talk about liquid entering will dilute the oil. Now, what do we mean by that? What do we mean by that? So, what we mean by that is if you've got liquid refrigerant, so this should be vapor only. And I'm saying vapor refrigerant only. If it were that you brought a bunch of liquid refrigerant into that system, the liquid refrigerant would tend to dilute. It would dilute that oil and not make it very, let's call it very good. It would not be a very good lubricant anymore. And that would be kind of a real shame, and it does create damage to the compressor. So that's kind of a little bit of a problem. Now, the liquid refrigerant entering should never really happen, and we have systems that should allow us to actually control that. Now, in the video or in the PowerPoint, we had talked a little bit about liquid entering may cause something called slugging. And what slugging meant, what we meant by that in that PowerPoint was that it was trying to compress a liquid, and now obviously that creates a problem. The oil return from the suction to the crankcase, that was identified right here, oil return. So, and that was item F. And then, of course, item G, the heat of compression. So every compressor is going to have this, where you take those molecules and you squeeze them together, and there's so much friction. It's almost like if you took your hands and you started rubbing them together, your hands would get warm. Well, refrigerant molecules, as we squeeze them together, they're almost doing that. They're rubbing them together and they're creating heat. And that's essentially the friction that creates the heat that goes on into there. So That's essentially called heat of compression. So that's the reason why the temperature of the vapor leaving these compressors got so warm. So heat of compression is a big part of that. So that's a little bit on the section of item number 10. So, and I'll stop this one to break these up a little bit and continue on with the next one after this.